Welcome to this talk on disconnection for the harmonic crystal with random conductances. My name is Maximilian Nitzschner and I'm currently working at the Current Institute at New York University. So in this talk I will present recent joint work with Alberto Chiarini, who is at the moment at TU Eindhoven. So the goal of this talk is to explain certain aspects of the geometry of random interfaces, where a d-dimensional random interface, where d is some positive integer, is nothing else than the graph of a random mapping phi, mapping zd, the integer lattice, to R. So in this case, the set of x phi x, where x is the point of the integer lattice, is a set in Rd plus 1 that describes an interface that has no overhangs or bubbles. So this you can see represented by this picture here. So we will study the geometry of such an interface by looking at its upper level set E bigger or equal to alpha, which is defined as the set of all points in the integer lattice for which the field phi is bigger or equal to alpha. So, and we will do so at varying levels alpha. So since phi is supposed to be a random function, this will constitute a random subset of ZD, which is a so-called percolation model. So to visualize this, you can see on this slide a graphic representation of the level set of this random function at varying levels alpha in dimension d equals to 2. So these are simulations done by Alberto Chiarini. And in 2 dimension, one may really think of phi as a random mountainous landscape, and the upper level set at level alpha describes the points at or above this height alpha, which of course is something that decreases as alpha increases. So if there is an infinite connected component in the level set, we will say that this E bigger or equal to alpha, this level set percolates. So of course, to say something specific, we will need to introduce a probability measure P governing this random function phi, and thus giving us a corresponding percolation model E bigger or equal to alpha. So here there is just another representation of the same picture, only this time showing only the points of the lattice Z2 falling in E bigger or equal to alpha. And you can see as alpha increases, of course, this set gets sparser and sparser. Okay, now to introduce a reasonable probability measure on the space of real functions on ZD, what we will do is we will consider a real function h on R to the ZD, which is called the Hamiltonian. And this Hamiltonian, in some sense, measures the energy of a configuration or interface phi. So the probability measure we will then consider weighs a configuration phi proportionally to minus the to exponential of minus h of phi. So what that means is that configurations with lower energy are favored. So this, of course, is still a heuristic definition, since here we are speaking about infinite volume, but this can be made rigorous by, for instance, looking at finite volume approximations and then setting the volume or sending the volume to infinity in a way. Okay, so, but now what is a natural choice to assign energy to a random height function? Well, one way would be to panelize large height differences between neighboring lattice sites. So one may visualize this somewhat loosely in this picture that you can see here on the left, where there are little springs attached to each of 2 neighboring lattice sites. And if there is a large height difference between 2 neighboring lattice sites, then this spring somehow gets stretched, and this adds to this energy. And we will choose to do this in a quadratic way, such that the Hamiltonian assumes this kind of form. If we sample phi according to P, which has this kind of Hamiltonian here, then what we get is a so-called harmonic crystal, or Gaussian free field, or discrete Gaussian free field, which we abbreviate as GFF. So this is kind of a homogeneous picture for a homogeneous crystal, and a very natural modification of this is to introduce like some kind of spatial inhomogeneity. So this means one can kind of think of replacing some of the lattice sites, or atoms, if you will, by different atoms, so atoms of a different type, which then gives the model a kind of spatial inhomogeneity. Now, mathematically, what does this mean? So this would kind of amount to introducing weights, or so-called conductances, between nearest neighbors, which we call omega. And we will always assume that these omegas are between lambda and 1, where lambda is just some constant between 0 and 1. So this is a so-called uniform ellipticity assumption. Okay, so if we do this, then the Hamiltonian that we obtain in this way will also take into account that the same height difference between neighboring lattice sites may actually amount to a different contribution to the total energy depending on the interaction strength. So if we do that, what we obtain is a modification of the GFF, which we will call the harmonic crystal or GFF with conductances omega. And here the terminology conductance comes from random walks on networks, but what one should really think of here is interaction strength or kind of spring constants between neighboring lattice sites. Okay, so after this slightly informal motivation of this probability measure governing phi, let us now give a precise definition of the harmonic crystal with random conductances. So for a fixed choice of omega, one can consider this weighted graph CD, ED omega, where ED denotes the nearest neighbor edges of the lattice and omega is just a choice of the weights. So in what will follow, we will always work in dimensions larger or equal to 3. So to determine omega, a good idea, if we want to kind of describe a inhomogeneous environment, is to introduce a probability measure Q, which we call environment measure, such that under Q, these conductances omega form a sequence of IID random variables that fulfill this uniform ellipticity assumption. And after having fixed this omega, we can then define this harmonic crystal with conductances omega, or this will then be the harmonic crystal with these random conductances omega, as the Gaussian field with zero expectation and covariances given by the green function of a simple random walk on this weighted graph CD, ED omega. So the important thing here is that this is like a model where the randomness comes in 2 stages. So first we sample in an IID fashion this environment or these conductances. And after we've done this, we put on this weighted graph CD, ED omega with a fixed realization omega, this field phi. So this is kind of very reminiscent of what happens in random walks in random environments in general. Okay, so now with the model rigorously defined, let us turn to its level set percolation. And in the case of constant conductances, this phase transition of the level set has been studied quite rigorously and to quite some detail in the last decade. And there are especially 3 critical levels that have been introduced. And in our work, we also have 3 critical levels for the percolation phase transition, which are kind of similar but slightly different in detail to the case of constant conductances. So the central parameter to describe the phase transition here is this so-called percolation threshold, which is this alpha omega star. And this is the smallest level alpha, such that the probability that the level set E bigger or equal to alpha percolates is still 0. So this is a level such that if we are above alpha omega star, essentially we have no infinite connected component. And below the level alpha star omega, one can show that there is a unique infinite connected component of E bigger or equal to alpha. Okay, so then there are 2 other parameters, which are this alpha star star omega and alpha bar omega, and they characterize respectively a strongly non-percolative regime for E bigger or equal to alpha and a strongly percolative regime for this E bigger or equal to alpha. So without going into too much detail here, above alpha star star omega, the connected components of this level set are supposed to be very small, so one has like a fast decay of connection probability. And below this level alpha bar omega, in the strongly percolative regime, one is kind of supposed to have a local uniqueness of these of large connected components of E bigger or equal to alpha. Okay, and the way that we introduce these critical parameters directly implies that they are ordered in this way. And then we also show in our result, building on previous results for constant conductances, or at least non-random conductances, so see Rodriguez, Nittmann, Popov-Rath, Drewitz, Brevo, and Rodriguez, that in fact this alpha bar omega is strictly positive and the alpha star star omega is finite. So an important thing here is that in our definition of these critical parameters alpha star star omega and alpha bar omega, we need a certain kind of uniformity over large boxes where we need some result on connectivity to hold basically. So let me not go too much into the detail, but the picture is this one, that there is a strongly percolative phase, a strongly non-percolative phase. And the important question is, of course, do these regimes actually coincide with the percolative and non-percolative phase itself? So in other words, are these three critical parameters the same? And this has last year been answered affirmatively in the case of constant conductances by these authors. Okay, so now let me come to this disconnection event. And the setup is as follows. So we will consider a compact subset A of a box of side length 2m, which has a non-empty interior. And we then study the event d alpha n, which tells us that there is no path in E bigger or equal to alpha connecting an to Sn. So this is this so-called disconnection event. And An is supposed to be the discrete blowup of the set A, and Sn is the boundary of the discrete blowup of this enclosing box. So here on the left, you can see a realization of the field where disconnection occurs. So there is no way to go from An to Sn via the set E bigger or equal to alpha. And here on the right, you can see an instance of the field where there actually is a path in E bigger or equal to alpha connecting An to Sn. So here, d alpha n, the disconnection event, does not occur. So the question we ask is, what is the large n behavior of this disconnection probability? And also, what can we say when we condition on this kind of event? And we will ask this question in a strongly percolative regime mainly, which means that this will be a kind of unlikely event. Okay, so now let's turn to the main results. And these are quenched asymptotic upper and lower bounds for this disconnection probability. So quenched in this setup means that these will be bounds that hold for Q almost every realization of the environment. Okay, so first of all, for alpha smaller than alpha star star, one has a large deviation type lower bound at rate n to the d minus 2 for this disconnection probability, where the rate involves the capacity of the set A, as well as the level and this alpha and the critical level alpha star star. We also have a upper bound of the same nature, but now with A replaced by the interior of A, and more importantly, alpha star star replaced by alpha bar. So both of these results generalize earlier findings in the case of constant conductances. So see, for instance, Snitman 2015, where this kind of question has first been studied in the case of the GFF with constant conductances. Okay, so now finally, let me make some comments on this result. So first of all, this capacity is defined for a closed or open bounded set B in Rd, or can be defined as the infimum of Dirichlet energies. And this matrix sigma hom that enters the picture here is the deterministic asymptotic diffusivity of the random walk on ZD omega, which comes from a kind of quenched invariance principle. So in a way, the capacity is the size of the set B as seen from a far away Brownian motion that has the same diffusivity asymptotically as the random walk on this weighted graph. Then furthermore, if these three critical parameters that I introduced earlier do coincide, which at the moment is open, and if the set A is regular in the sense that its capacity is the same as the capacity of its interior, then our quenched upper and lower bounds actually give us the main asymptotic or the principal asymptotic decay rate of the disconnection probability, at least for alpha smaller than alpha star. And this, of course, again for Q almost every realization of the environment. And finally, in this case, so again, if we can show that these are the same, which at the moment is open, conditionally on the disconnection event, one can also show that there is a certain push down of the field to a local level for which we can determine explicitly. So what that means is kind of shown in this picture. So the Gaussian free field, if we condition it on this unlikely disconnection event, is supposed to lower itself to a kind of local level that depends on A as well. Okay, so that actually brings me to the end of my talk. So in this slide, you can find the references that appear throughout the talk, and I thank you very much for your attention.